Hello everyone, today we're talking about bases for subspaces, and in particular two of our favorite subspaces, the null space and column space of a matrix. Let me just recall from last time what is a basis. So a basis for a subspace H is a collection of vectors, let me call it B. Let's say these vectors are B1 through Bk, such that two things happen, right? B is linearly independent. So this is the kind of like not too many vectors. And then B, well, let me write it this way, H equals the span of B. So there's enough vectors in your collection that everything in H can be written as a linear combination, but there's not too many vectors that you have any dependencies, any redundancies. Okay, so today we're going to talk about bases for subspaces, and let me do this with an example. So let me start with three vectors in R3, 0, 2, minus 1, 2, 2, 0, and say 6, minus 16, minus 5. And let me let H be the span of those three vectors. So as you know, one way to always cook up a subspace is to take the span of a bunch of vectors. So, you know, we're in R3. This is a pretty down-to-earth example. You've got three vectors, V1, say V2, and V3. And I'm taking all possible linear combinations, the span of those three vectors. Now, what I want you to note is that the vector V3, in fact, is a linear combination of the other two. It's 5V1 plus 3V2, right? Because 5V1 would be 0, 10, minus 5. 3V2 would be 6, 6, 0. And if you add that together, you get 6 minus 16. Hang on, so this should be 5. Oh, so this should be plus, sorry. Copied down wrong. So now it is actually equal to 5V1 plus 3V2. It's 6, 16 minus 5. Yeah, right. Okay, so what this is saying is that this vector V3 is already in the span, it's already a linear combination of these two vectors V1 and V2. I can achieve V3 as a linear combination of these other two. So in other words, if I look at H, which was the span of V1, V2, V3, I didn't actually need V3 to make that span. This is actually equal to the span of just the first two. Okay? And also, of course, we know that the collection V1, V2, V3 is linearly dependent, right? Because whenever you can write some vector as a linear combination of the others, that's a dependent set. Whereas when I threw out V3, I get just these two vectors, and that forms an independent set because I can see they're not scalar multiples of one another, right? So V1, V2 is linearly independent. Okay, so why am I saying all this? Well, what this implies then, maybe you can anticipate where I'm going, is that a basis for H is given by, well, V1 and V2, because now I have a independent set, right, whose span is H. So you kind of started with three vectors that defined H. I just popped out this V3 and I got a basis. So this is actually an example of a more general phenomenon, so I'll just write this out now. So fact, suppose, the more general setting, we've got, say, V1 through VP, and let's say H is the span of those vectors. So, I'm not telling you where they live now, but I'm just saying that we have a bunch of vectors in a vector space, and we take a span of those. There's two things I want to point out. If some vector, let's say Vj, is a linear combination of the other vectors, then removing Vj, like we did before, preserves the span. The span does not change when I take away, right? So just here, when I popped out V3, I got the same span as what I have before, right? That's the first fact. And then the other fact is kind of related. As long as H is not the zero vector itself, so remember, well, one example of a subspace is just the zero vector itself, but as long as we don't have that, then some subcollection of, well, that set you gave me of V1 through Vp forms a basis. So what that's, what that's saying, again, I'll go back to this example here, is that you gave me these three vectors and you said H was the span of those three. What I do is I just find one that's a linear combination of the others, pop it out, and then I'm left with V1 and V2. And then what I do is I keep going. If V1 and V2 was a dependent set, I'd pop out one of those vectors and I'd keep doing that until I get a linearly independent set. Here I was actually already done at V1, V2, and what you get is a basis. Okay, so that's a nice property to have. We're now going to apply this. Applications to, well, the column space of A. So, as you know, right, column space comes from a matrix. Let's suppose A is an m by n matrix. I'm just going to do an example here, kind of a big example that we're going to use to illustrate this idea. Suppose we have this matrix here. So 1, 3, 2, 5, 4, 12, 8, 20, 0, 1, 1, 2, 2, 5, 3, 8, minus 1, 5, 2, 8. So this is a 4 by 5 matrix. And I want to know a basis for the column space, and actually I'm also going to ask for a basis for the null space eventually. In both cases, you want to reduce to the echelon form at least. I'm going to press my magic row reduce button, and notice that, well, I'm going to write down the reduced echelon form, which looks something like this: 4, 0, 0, 0, 0, 1, 0, 0, 2, minus 1, 0, 0, 0, 0, 1, 0. Okay, so that's the reduced echelon form. Let me circle the pivots here. So pivots are in columns 1, 3, 5. Now, here's a fact that I'm not going to say too much about, but the kind of magic that happens is that, this matrix here, this reduced echelon form, is much different than this matrix. But the observation is that linear dependencies in B are the same as those in A. Okay, so what do I mean by that? Well, notice, for instance, just maybe an easy observation here is that this second column, right, e.g., B2, the second column, is just 4 times B1, right? That's clear. But look at that. That's the same thing that happened up here, right? The second column of A was also 4 times the first column. And, another one that you could see is that if I look at B4 here, the fourth column, that's clearly twice B1 minus B3, right? If I look at this vector, it's twice this minus once that, because these are just, those standard basis vectors. And notice that the same thing happens. So if you look at the fourth column here, it's going to be twice B1 minus B3. So twice this guy minus this. So, 2 is 2. 2 times 3 minus 1 is 5. 2 times 2 minus 1 is 3. 2 times 5 minus 2 is 8. And so that's pretty great for us, because if we want to know what's an independent set, well, that's going to be correspond to an independent set of this reduced echelon form, and it's clear that the pivot columns are those, right? A maximally independent set would be the pivot columns here, because those are just zeros with a single one in some row that's different than the others. Okay, so what's the punchline of all this? Is that, let me just say this as a fact, a basis for the column space of A is given by the vectors of A corresponding to pivot columns. Okay, so here in our example, a basis is, well, let me go back to here. So what are the pivots? I should have circled, though. The pivots here are, right, those three. So it's the first, third, and fifth columns. Just make sure you're taking the columns of A. It's not of the reduced echelon, right? It's of the A itself. So it's the first, third, and fifth columns. Okay, so the pivot columns. And again, don't take the pivot columns of the reduced echelon because those are clearly not a basis, right? If I look at the 1, 3, 5 columns here, those all have zeros in the last entry. And so that's definitely not going to be a spanning set for the column space because, well, you got non-zero things in the last entry. Okay, so just while I'm here to wrap up, we can also get a basis for the null space. And so let me just say, what about the null space of A? And here's the next fact. This is, again, something we've already been doing kind of behind the scenes, is that a basis for the null space of A is given by those vectors in a vector parametric description of, of the solution set, say, of the homogeneous AX equals 0. So remember, the null space is just by definition the solution set of the homogeneous. And we've already been doing this. We've been talking about how to describe the solution set in terms of linear combinations. And if you think about it, what we were doing is actually finding a basis. So again, let me go back to our example here. So here's our example. So here's where I really need, let me say, I need the reduced echelon for this. I should point out that when I was going back to when I was talking about the column space, I only need the echelon form here because I only need to know where the pivots. Okay, but for the null, for the basis of a null space, I need actually this reduced echelon. Why is that? Well, remember, once I have the reduced echelon form, I can write the solution set. So, usual story, I'm going to write this as my 5 variables. And what I see here is that 2 and 4 are free, so I'll write those down. It looks like x1 is the same as minus 4x2 minus 2x4. x3 is equal to x4. x5 is 0, right? x5 equals 0. And then the usual story, I break this up into my x2 stuff plus my x4 stuff, my free variables. This looks like a minus 4, 1, 0, 0, 0, and then a minus 2, 0, 1, 1, 0. And so, again, this is why I drilled this into you guys, is that when I have a parametric description of the solution set, it says a lot of nice things. And this in particular tells me that, since the null space is given by all possible linear combinations of these two vectors, it turns out these vectors will always be linearly independent. And so a basis for the null space is given by, well, those two vectors. So minus 4, 1, 0, 0, 0, and minus 2, 0, 1, 1, 0. Of course, these are vectors in R5 because the null space is a subspace of R5 here. Of course, the column space basis consisted of vectors in R4 because column space is a subspace of R4. Notice that the basis for the column space has 3 vectors corresponding to the pivots. A basis for the null space has 2 vectors corresponding to the free variables, right, the non-pivots. And that's, again, something we've seen before. We'll see that again, make that more precise. But that's it for today. We'll see you next time.